Okay, hello and welcome everyone. And I can't see the room over there, but I can see the projector screen. Okay, and I see you there, Shelley.
I'll turn you around.
Let's do that.
Part of it. I'll probably break everything if I do this. That's good. That's good. Okay.
Okay, great. Hi, everyone. Thank you all for coming. Yeah, so as I said earlier, just, you know, that I think this is pretty informal. We want feedback from everyone. We want to, you know, outline some information for all of you. Please just jump in with questions. Shelley, feel free to jump in and take over here as well. So we have a few slides here to just kind of go through a little bit about what Liger is, its capabilities and current status, and talk a little bit about the science, the broad science that we envision with Liger. And we'd really like to hear any input on what you would want out of this instrument, specific capabilities that you want it to have, and science that you would want to do with it. Okay, so we'll go through these slides. First thing I thought would be good to clear up is what is Liger, or what is a Liger? So I didn't know this until, you know, not that long ago. Liger is a real animal. It's a cat. It's the biggest cat in the world, and it's the hybrid of a male lion and a female tiger. And here's a picture of an actual Liger. This is Hercules. He weighs about 1,000 pounds, lives in South Carolina, I think. If you go the other way, a female lion, male tiger, it's called a tigon, and they're smaller cats. So fun things you learn. This is true. So that's what a Liger is. It's a big hybrid animal. And Liger, the spectrograph and imager, is also somewhat of a hybrid. And so that's the name. Liger is not an acronym. It's a nice name. And it's a hybrid design between the Iris spectrograph for TMT with Keck-AO instrumentation. So it's a sort of a TMT spectrograph built for Keck. Liger leads, Shelley Wright at San Diego there is overall PI. And then there are a number of us involved across multiple UC campuses and at Keck Observatory. Shout out to Aaron Brown as well at San Diego as the project manager. So this is the team, wonderful people. Find and chat with any of us anytime. And let's talk about Liger, the instrument here. Here's a little rendering of it, and let's dive into the guts a little bit and tell you what it is and what it can do. So what we'd like to do today is again, you know, some overview, design and capabilities, get your input on design, on science cases, any new idea, any discussion you want to have, and any questions you want to ask. Again, just jump in anytime. So I thought I'd start with a little motivation. Why build Liger? So Liger really supersedes Keck's current AO spectroscopy capability with Osiris. So Osiris has an imager and an integral field spectrograph, but it's you know, of course, bound in many dimensions. So the wavelength doesn't go below a micron and is not so great at shorter wavelengths. There's a single spectral resolution mode. The field of view is modest, and it's kind of set by the Hawaii 2RG detector that's in there. Another thing is that the Osiris is pretty limited on the coarser scales, and the 100 milliarc second mode was kind of a late add-on and feature. It wasn't really designed for that, although it now gets a lot of science use. Certainly I've been using the 0.1 arc second mode to do a lot of high redshift galaxy work. So Liger would replace Osiris and improve upon all its capabilities, really letting us get to all the science that's just out of reach, or maybe quite a ways out of reach with Osiris at the moment, and take advantage of the Kappa adaptive optics upgrade to the Keck-1 telescope. So Liger would really take advantage of the new AO capability that we would have, particularly with the LGS AO with Kappa. And as the Liger design, particularly the spectrograph, is basically drawn from the design heritage of Iris for TMT, which includes a slicer and lenslet integral field spectrograph. So relatively moderate design and cost gets you a very powerful instrument for Keck. Here we go. So here's the overview, the nuts and bolts, so to speak, 3D, and then the optical path. So you have your beam coming in, feeding an imager, and here's the optical plane up here. So you have a 20 arcsecond field of view imager, and then two different integral field spectrographs. The IFS and the imager operate simultaneously, but you don't get both IFSs. You pick either the slicer or the lenslet. So you use a mirror to pick whether you want the coarser, the larger fields with the slicer, or the more finer fields sampling the diffraction limit with the lenslet, which is more similar to the current Osiris design. There's your optical path. Just a little bit more on what you can do with this. So you choose one of the spectrographs plus parallel imaging simultaneously. The instrument operates from about 0.8 microns all the way out to the thermal K band. Same wavelengths for both components, imager and IFS. The imager, you have your 20 arcsecond field, 10 milliarcsecond pixels. So quite similar actually to the current Osiris imager specs. The IFS, you have smaller lenslet fields, larger slicer fields, with commensurate spatial sizes, and selectable resolution. So not just a single mode, but you can pick between a resolution of 4,000, 8,000, or 10,000. And then different fields of view and such, depending on your wavelength. We'll get to that in a bit. So just some specs on the plate scales, basically, for the IFS. It goes from 14 milliarcseconds all the way out to 150 milliarcseconds. So a factor of 10 range in the sampling scales, depending on whether you really care about diffraction limited sampling or surface brightness sensitivity. And you can select this to within about a factor of 2. In the coarse scales, you get up to quite a large field of view, 13 by 7 arcseconds, essentially. And so pretty broad capabilities here. This is, of course, a facility class instrument and capable of doing a whole lot of different science. Pretty much all the Osiris or NERC2 science that we're doing now, up to the near infrared plus more. A little bit more on the observing modes. This table can be a little complicated, but basically, essentially you have a trade-off between what field of view you want, what spatial sampling you want, what spectral resolution you want, and the band pass. So you can have a large field of view, say with a 5% wavelength band pass, which would be sort of a narrow band. You can have a full broadband, say J, H, or K at once with a 20% band pass with a smaller field of view. There's also an ultra broadband mode where you can get, say, the H band plus the K band entirely at once. Again, with a smaller field of view, although you can get this coverage with up to about a 7 by 7 arcsecond field of view at a resolution of 4,000. And then you can also select the higher resolution modes and trade off a lower field of view for that. So wide range of capabilities because you get to select essentially all 3 of these parameters. Really here, the introduction of the higher resolution modes is probably the biggest change relative to what you might be used to if you're using current integral field spectrographs. Okay, let's see. So a couple of things on the specs. Oh, sorry about that. Here we go. This is one of Shelley's favorite plots here, the étendue couleur. Basically, Liger has very wide spatial area and spectral bandpass with a larger format detector that allows this, and excellent image quality. So you're getting really good data and a fair bit of it. This plot shows kind of essentially the pixels you're getting, so the field of view multiplied by the bandpass as a function of spectral resolving power. And so with Liger, you get a range of resolving powers and a very good field of view and bandpass here. And then these other, grayed out instruments down here are comparable adaptive optics fed integral field spectrographs. Here's Osiris down here, for instance. So you're really getting a lot more data, a lot more science potentially out of Liger. And then over here, for those who really care about imaging quality, high Strel, diffraction limit, this is the design spec of the wavefront error across the imager field and the lenslet spectrograph and slicer spectrograph fields. And the takeaway here is that, that it's really very low wavefront error. You're getting down across almost all the field, having wavefront errors below about 30 nanometers. So this really enables diffraction limited sampling and good resolution, basically limited by your AO system, all the way down to into the red optical, sort of at 0.8 microns or so is where your wavelength coverage would cut off. Okay, that's most of it for the instrument specs. I was going to mention a little bit about the sensitivity and some examples of what we envision. Any questions on the specifications, capabilities of the spectrograph so far, or the imager?
I have a quick question. Why is KMOS so low in the Entendu plot?
Oh, I think that's probably just a single IFU.
Okay, do you have it multiplied by 24? I see.
Yeah, if you multiply by 24, then, you know, it would be up here, then we wouldn't want to, you know.
Got it.
Is that right, Shelley?
Yes.
Yeah, yeah, so that's one KMOS IFU, and then it's multiplexed. Good point. Okay, so this is,
We got a question in there.
oh, great, thank you. Sorry, go ahead.
The spectral can be taken from the spatially resolved
The question was, are the spectra across the 2D spatial plane, I think? Yeah, the answer is yes. So across the field of view, at every location in that pixel scale for 14, 31, 75, 150, you get a spectrum along for the ride. And so in an integral field spectrograph, you should think about it as like how many spectra you are dispersing across your detector. And in this case, we get, you know, up to like 3,800 spectra, right, dispersed. That's a great question.
Only in the lenslet and the slicer.
Yeah, this is a, you know, this cartoon, you know, diagram on the left is just showing maximum coverage. So that's to answer Twan's question. It was a way to show field of view versus, you know, total percent bandpass you can get from these modes compared to the current ground-based IFSs. You know, you can cut and carve this different ways to make it look different ways. It's not my favorite plot. My favorite plot's not shown. Attendu color would multiply that by the Attendu of the telescope, which then makes the plot go really good because you have a 10-meter telescope.
Hi, Tucker. It's Sean. I just had a basic question about qualitatively, like the IFS be sitting, you know, at the same PA, just up against the imager, like different than currently Osiris, that being, you know, like 20. Qualitatively, that decision that was made up.
Tucker, the questions about field location of the imager and the spectrograph across the focal plane from the AO system.
I guess.
Why are they next to
Yeah,
each
do you want me
other?
to, I know, you want me to answer? You want to go ahead?
You could go ahead, yeah. But yeah, you're talking about because with Osiris, the spectrograph and the imager are quite a bit separated in the plane, right?
It's a great question. So the big difference between Liger and Osiris is that the way to describe it is that the imager and the spectrograph are what's called parfocal, right? They're in the focal plane. So if you have an image of the detector, there's two pickoff mirrors that are right butting up against it as close as possible. So it's in the focal plane of the KEKAO system. And Osiris was not designed that way. So it was an add-on. So you have a pickoff that goes off. And it means that you're never quite in focus. In fact, that's an issue with Osiris right now, is that the focus for the imager and the focus of the spectrograph is slightly different. So you want it to be in the same focal plane,
Yeah.
Especially if you're interested in Sean and PSF reconstruction. And then the next question really should go to Tucker. The science team spent a ton of time figuring out where they should live next to each other and how to get the wavefront arrow, the map it is today.
Yeah, and so this is Rainey Kupke's brilliant design where you have these right next to each other. You're taking advantage of your same, you know, if you're using LGAO or any AO, your same corrected field. And the IFSs are actually, there's a very slight displacement so that you manage to get simultaneous focus in both, well, both spectrographs plus the imager at once, so that you really are getting that very good image quality across your simultaneous imaging and spectroscopy in the same exposures.
Chuck, are you going to talk about the astrometric precision? Do you have a map of that?
Oh gosh, I do not.
Okay, I was just curious.
Yep, but thanks. I know that's an issue. Yeah. Okay, any others here?
Get one more.
So when you do imaging at one of the instead of slicers at the same time, how much light do you?
No, they're separate fields of view. They're actually just right next to each other.
They're not preserving the
No, but you could move them between. Like if your star is here, you're like, I have you here, imaging here, now imaging. Your eye is looking at sky, and so you can bounce back and forth.
So you're seeing the same light.
They're pointed at different parts of the sky, so you can't look at the same thing with the imager and the spectrograph at the same time.
Did you guys get that in Zoom land?
Trying to type it in Slack.
Okay, thanks, Joe.
No, it's kind of hard to hear you, Shelley.
If you jump onto the Breakout Liger Slack channel.
Yes. Yeah,
you can see
saw
the
that.
questions and answers now there.
Okay, but yeah, to clarify the last one, it's you're getting different light. This field here, that's really essentially your sky. And so you're looking at this part of the sky with the, say, the slicer, and this part of the sky with the imager. If that makes sense. Is there stuff in this Slack that I should look at, that we should bring up?
Not yet.
Okay. Great. All right. I hope that clears things up. Should we talk about sensitivity, instrument performance, and such? 3, 2, 1. Okay, let's go. So this is a plot showing, you know, the expected sensitivity of Liger, you know, plus the Kappa system in comparison to sort of the instrument landscape. So the green curves are showing Liger expected performance, basically expected limiting magnitude, you know, for some fiducial AO performance as a function of wavelength. Here we're looking at the finer spatial scales, in this case, the 14 and 31 milliarc second scales, and over here at the slicer scales, you know, in comparison to other instruments sampling of order 100 milliarc seconds. And so all of these other curves are other adaptive optics fed integral field spectrographs. You have Osiris in blue, for instance. Down here at, you know, 1 to 2 magnitudes deeper is where we expect Liger to be. And then this bad boy down here is James Webb Space Telescope, where, you know, it's in space. But so Liger would really get, you know, quite a bit deeper than any other current or near future AO fed integral field spectrograph. Let's see. So that's the sensitivity curves. Is that it? Yep. Okay. So then here are just some examples of what Liger data would look like, you know, based on the Liger simulator that we have. Here's a very nice example that I think, Tuan, you put together on the Galactic Center. So here's Sagittarius star, here's the Osiris field of view, lots of stars. And here it is in comparison with the Liger field of view at comparable spatial sampling. So this is with the lenslet and the 31 milliarc second sampling. You get this nice, great big field. which really can be a huge gain in a lot of cases, I think. And then the panel on the right is showing the difference when you go from the current spectral resolution of Osiris at around R of 4000, which is also the Liger R of 4000 mode would be similar. And then in green is the higher resolution R of 8000 mode with Liger, where in this case, you can see the difference of really resolving many of these different spectral features. So if you're doing, say, stellar spectroscopy, and you really want to resolve your favorite absorption lines, or if you're doing emission lines and you really want fine kinematics, then this high resolution mode can really be transformative, even just going a factor of 2.5 upwards. I'll just preemptively say, so Liger is designed up to a resolution of R of 10,000, and we're not planning to go to higher resolution than that. I know there's science cases that would love to have R of 30,000, but that's just not in the works for this spectrograph. So up to 10K. Here's another example of a high redshift galaxy. This is actually I would call it a moderate redshift galaxy. This thing's at redshift 1. Here's the field of view of this is the smaller slicer field of view with the high resolution mode, the R of 8000 mode, and it fits nicely. You can go to R of 4000 and get twice the field. And what's remarkable about this is that this is simulated performance for a 2-hour exposure in the J band with Liger and with the Kappa AO system. And you're really getting excellent sensitivity to, say, map H alpha emission in Redshift 1 galaxies. We can't really do that today because we just don't have the sensitivity at these shorter wavelengths, in this case, about 1.2 or 1.3 microns. So, and getting back to, I think, one of the questions earlier, here's your field of view in the spectrograph. This is a 2D map, but each one of these pixels has a complete spectrum associated with it. From that, you can do things like measure, say, the velocity field from, in this case, emission line kinematics. So that's the kind of data we'd expect to get in just a couple of hours. One more example. This is a simulated performance of a lensed quasar system. It's actually been observed with Osiris before, and the blue is the Osiris spectrum of one of these images, actually this fainter one, this image D, it's kind of your limiting case. And then the green, and this is in units of photons per second per micron. The green is kind of showing the increased sensitivity that you get in particular with the slicer spectrograph. And in this case, it really lets you get a lot more photons or get a lot more sensitivity to those photons, detect things like the narrow line sulfur emission. So I think that's the last example slide, but another point here is that we do have a fully functional simulator that Niels Rundquist at San Diego has been running. And if anyone really wants to see exactly what Liger can do, well, you can mock up a data cube, send it to us, and we can run it through the end-to-end simulator and show you what that would look like, what kind of information you'd be able to extract.
Tucker,
So
we have
yep.
a lot of people here, so maybe you should explain what that quad lens thing is on the left.
Oh yeah, sure. Thanks. Yeah, so this is
doing there.
what is this thing? What are these points? Yeah, this is really cool. This is so A, B, C, and D are all images of a high redshift quasar, and this G thing in the middle is a galaxy, a massive galaxy that's acting as a strong gravitational lens, and it's splitting the light from the quasar into 4 distinct multiple images, each of which take a different path through space-time to reach our telescope. And this is very powerful in this case for cosmology, because of the way that the different paths that each of these light rays essentially take through space. So each one takes a different amount of time to reach us here on Earth, and you can monitor variability in a quasar, use the time delays, and geometry to actually figure out the expansion rate of space-time. You can use this to measure the Hubble constant, essentially. Or really, you measure the geometric distance, and that gives you the Hubble constant. The other cool thing is that they're, again, intrinsically all the same object. They're lensed. Lensing is gravity, and we think we understand how that works. And that gives you clear predictions for, in a relative sense, how bright each of these images should be relative to one another. And what's really neat is that if this big galaxy is sitting in a big dark matter halo with a lot of subhalo structure and little dark matter substructure, you can use the precise positions and fluxes, especially the fluxes of these different images, to look for dark matter, small scale perturbations caused by dark matter subhalos. So you can use this to test dark matter theories. I don't know, this is probably too deep, but it's really awesome, the kind of science you can do. And one of the big motivators here is with Liger, you're really getting 4 times the field of view as Osiris, and you can just observe these whole systems, which, you know, you really struggle with right now. The smaller ones you can probably pack in, but this object you can't actually get with a full Osiris field of view. Let's see. Yeah, any questions, thoughts here? Oops. Okay, again, so jump in with any cues. Here we'll go ahead and let's talk a little bit about the current Liger activities, the kind of timeline envisioned, current status. So, you know, big thing here is the Keck science meeting. We can talk a bit about the science team activities. So we have a pretty big and really amazing science team for the Liger instrument. And the science team's been involved in defining the top level requirements for the instrument that flow down, you know, what science do we want to do? What technical requirements do we need to meet, you know, to do that science? And then how does that flow down to the instrument design and things like the wavefront error and such. Of course, as this project goes along, there'll be a lot more work to, you know, refine that and update and actually verify that we ultimately meet these requirements to do the science. Some more specific things we're doing is prioritizing the selection of gratings and filters. So the wavelength ranges and exactly which spectroscopic modes. So essentially what wavelengths do you want or need to have R of 10,000 resolution? At what wavelengths do you want resolution of 8,000, but you don't necessarily need 10,000? So those are trade-offs that we have to look at from the science perspective. And so, for instance, any feedback input on this, you know, would be very valuable as we go along and plan the ultimate capabilities of the instrument. If there is a great need for, say, narrowband imaging filters, that's something that we want to know. A possibility that we've looked into a little bit is, so we can't have a full-on coronagraph, but a pupil plane coronagraph or other pupil plane optical element could be incorporated into the instrument. So for high contrast work or small angular separation work, that's a possibility. Okay, another thing is mentioned, we do have the Liger data simulator. All these cool science predictions, images that we've just seen have come out of a simulation of what we expect Liger to look like, the data to look like. And we can run that basically for any arbitrary field at this point, I think, in any of the instrument modes. So that's in a nutshell, some of the main science activities associated with the instrument. As far as instrument timeline itself, we are literally right now submitting a proposal to build this thing to the National Science Foundation. So in September 2021, right now, we're putting in a proposal to the Mid-Scale Research Infrastructure Program with NSF. having passed the pre-proposal process a few months ago, we're now going for the full one. If all goes well, construction would start in early 2023. Right now we're, it's an advanced state of design. This is kind of based off of many years of heritage with Iris and such. But this could, shovels could hit the ground, so to speak, in early 2023. And the first light would then be projected to about 2026, with science happening in the 2027A semester. Is that right, Shelley? I'm pretty sure I got that.
I think it's 2027B would be science release, but
Okay. Yeah, so it might be commissioning and
Yeah.
something like that. Yeah. Okay. So that's basically current status. Hoping for some good news for NSF over the next N months, and then we'll get going and get this thing delivered to all you wonderful people. And kind of last thing to note, here's a snapshot of the Liger science team. I'm sorry, I had to make the text really small to actually fit everybody on here. But we have a lot of great people representing a lot of great science from many different institutions, both within and beyond the KEP collaboration. We welcome input, of course, anytime. And if you're interested in getting involved and helping, define the science requirements and capabilities, please get in touch. You can email me and let's chat. I'm happy to. And I think that's it. So I'd like to open that up to any discussion, questions, comments that anybody has about Liger, the instrument, capabilities, etc.
Hey, Tucker, this is Lee. I had a question, a comment. Can you hear?
Yeah, I hear you. Go ahead, Lee.
Okay, good. Thanks. Can you give a little more information for people who might want to send you some beautiful cubes that could be sent in, like what kind of format or something, or how would you like to get them, or just a little more specifics, or maybe you can put it up on the page or something. I'm not sure.
Certainly, yeah. I can say, like, for this one, for instance, yeah, this was, we started with a sort of simulated 3D FITS file, noise-free, basically a any kind of three-dimensional array of data, or combination. I think in some cases, for this, I think we take kind of the two-dimensional structure and then input a 1D quasar spectrum that gets kind of multiplied by the flux in each pixel there. So yeah, it's best if you have some combination of the two-dimensional field, at least a 2D flux map, and then the 1D flux of everything in there, or a full-on 3D array would be even better, would be ideal.
Okay, so there's a little flexibility, and you're willing to work with people that might want to sort of give it a shot, right?
Yeah, definitely.
Okay, good, thanks.
Yeah, thank you.
As you know, it's units. So the hardest part about, simulations is, one, you want an intrinsic image that's better than what you're going to simulate, right? And so that's often hard because the resolutions here are pretty darn good. And then the second thing is, as long as you give us things that have units that make sense, then we can usually do it. Yeah.
Yeah, that's a great point. You definitely want to give us the flux calibrated version.
Tucker, I had a question. Is it the same exact wavelength coverage as Osiris, or can you remind us if there's any additional support at the blue end as we keep upgrading the AO system?
Yes, so for JH and K, you could think of it as more or less the same wavelength coverage, I think. Could vary a little bit depending on exactly the dispersion of each optical element across the detector. And then it goes down to shorter wavelengths. So Osiris cuts off at a micron. And for Liger, this would go down to 0.81 micron, I think, is the bluest we can get. So that would be an additional chunk of wavelength that's not accessible with Osiris right now.
And that's the imager and spectrograph?
Imagery and spectrograph, yes, exactly. So both cover the same length range.
The imager will have imager set filters, right, which aren't 20% bandpass, but the spectrograph, which BB means for broadband, are specialized filters that you guys may be familiar with if you use Osiris. The difference in the case between like Z and Y there is that through the grading blaze function and how the spectra get dispersed, we have to clip the ends a little bit differently than you might be used to. And we looked at optimizing that clip to make sure on the blue end, the reason why the science team asked to get to 810 nanometers to get to the bluer side of calcium triplet. So we optimized the grading blaze function to make sure we get those guys on the spectrum, on the detector nicely. So the JHK are kind of your traditional 20% band passes. If you've used Osiris before, the Z and Y for the spectrograph are slightly different. Well, in this case, the Z doesn't even exist. So for the other.
Yeah, that's right. What the Z band in Osiris is really in the Y band here. So this blue is totally new.
Yeah, thanks, Tucker.
Sorry.
Osiris team mislabeled a filter. So this gets super confusing. So in Osiris, it's labeled capital Z, but everywhere else in the world it's Y. And we probably should have updated the Osiris, documents, but now it'd be even more confusing. So Y in this case is Osiris is Z. Sorry, guys.
I saw earlier slide showing something like achieving an RMS wavefront error of 30 nanometers. Is that so? It sounds pretty amazing. Is that are you guys setting that as a science like a requirement of system or?
So that map, can you go to that map? So that's the RMS wavefront error through the whole spectrograph, through the entire system of Liger.
Without the AO system.
Without the AO system.
Okay.
Yeah. And yes, so Osiris at the reason why we go to the that low wavefront error to get even on Osiris, you can see it changes for the slicer, is to get to less than 40 millimeters. Using the error budget to essentially get to the diffraction limit and make sure that we're using the best of the AO performance.
Okay, great. Okay, yeah. A little confused, so it's not with AO.
Yeah.
Okay.
And the KEC AO system, you can optimize a little bit, right? So you can kind of redirect where your best quality is and across that field.
Would there be, given that this is designed for kappa, would there be a difference in performance for a natural or laser kite star? Or
so the map here has nothing to do with the AO system.
Okay.
It's just the wavefront error for our instrument. And the answer to your question is yes. You would get different performance levels. And the sensitivity curves that were shown there were kind of average conditions for LGS.
You mentioned picking potentially some narrowband filters. And I was curious what the boundaries are there, like how many there could be.
We only have a few slots available. It's the filter wheel can hold up to 51 filters, which is a lot. So there will be a few. We have a few 1% filters stacked, and I suspect those will be very interesting meetings to see which 1% are selected. Yeah.
Yeah, that's right. I think we have of order 10, I think a little bit less than 10, maybe 7 or 8 slots, give or take, that we would have for narrowband imaging filters, assuming that we want to have broad spectroscopic coverage with the 5% bandpass spectroscope filters.
Like on that, some of the things we hear from the science team is like a methane filter is like on and off. So you oftentimes need like an on filter for the methane. These are for like, low mass stars, brown dwarfs, and then an off filter. So if you do JHK, then you times that by, 2, you're already up to 6 filters there. And then of course for galaxies, you may be interested in Bragg again, caching data. So there will definitely be a pretty large trade study and that goes to the science team on final selection. Tucker's already gone through, I think, 2 rounds of this.
Yeah, I think we've done 2 rounds. I'm sure we'll have to do a couple more.
It'll be the round and round and then procurement, basically. No going back.
Okay, Matthew, I see you got your hand up.
Yeah, so I'm looking at the plot you're showing right now. The 10K and 8K have the same field of view bandpass number. So why is it that anyone would ever use the 8K?
The 8K gives you a little better sensitivity.
Ah, okay.
Yep. And both raw throughput sensitivity and then if you don't quite need all the way to 10K, then you're a little bit better off. So I think the instrument performance, it's generally does well at 8K, and then you start losing a little bit of sensitivity and throughput dropping off as you go up to the 10K. So I'd say the 10K is a little more specialized mode, and the 8K would be more of the workhorse high resolution, actually.
And at 10K, how many pixels makes a spectral resolution element?
Oh, I'm not sure. Shelly, do you know?
One slide up.
There you go.
So you can go to the left column, Matthew.
Yeah.
That gives you your spaxels.
I think he's asking how many
I think spectral pixels.
spectral resolution element.
Oh,
Is it
you
critically
can get
sampled?
you can get the full broadband. You just lower your field of view.
But for a line, are there 2 pixels across the resolution?
Yes.
Yeah, so it's
yes.
NICO
It is
sample
NICO
at
sample.
10K.
Yes. Yeah. Yeah, good question. Thanks.
Yeah, and at 8K and 4K, of course.
Yeah, what our team did, in fact, Arun, I think, is on the line. He spent a lot of time with the Zmax model and modeled, the grading blaze functions and dispersed the spectra, and then sampling with the detector. And the reason why we're interested in that, one is because we have to optimize our grading selection with our filter band passes, but we're interested in the spectral extraction, right? Because that dominates your noise for both the slicer and the lenslet for spectra and IFS. So you're looking at the spacings of spectra, but we have that all modeled, and that's what you're seeing.
So I have a related question. In the sensitivity curves, anybody who's used Osiris in complicated scenes knows the sensitivity is not what it's quoted to be because the spectra overlap. And they don't overlap as much in Liger. So I was curious whether your sensitivity curves in here in Osiris were sort of isolated point source perfect Osiris sensitivities, or is the gain going to be actually larger because the Liger spectra are just separated more?
So Jessica just asked a very detailed
Sorry.
question.
Great question, though.
I was like, wow, okay. The answer, Jessica, is that the sensitivities you included here, Nils did include correlated noise in the 100 milliarc second mode of Osiris, because it was kind of a fudge factor that we did, but it is included for the 100 milliarc. So the question she had is that in lenslet spectra, you pack the spectra really close, so all the spectra are basically on top of each other. And when you spectrally extract, you have to take all your dispersed spectra and make it into a cube. And you run a deconvolution routine on that. And so you were correlating the noise. And so the difference is the Gemini planet imager, right, uses a lenslet integral field spectra, but they separate their spectra so much because they want that clean extraction. And so there's a trade-off with a little bit of noise and field of view for any IFS actually. So that was the meat of Jessica's question.
Sorry.
What leads to the biggest range in the change in the sensitivity between Osiris and Liger? you know, if you're getting a few extra magnitudes, is it kappa? Is it better optics? Is it happier detectors?
It's kind of all of the above.
Okay.
So it's, you know, one big difference between Osiris and Liger. Osiris has a single fixed grading, so you're operating in higher orders and multiple orders. Whereas Liger is operating in individual grading. So we have a 14 grading suite. And so you get higher throughput there. And then optics and detectors. And then, you know, we shouldn't fudge this, but there is a plus kappa there. So
Yeah.
But that's even, you know, Gurmos is a future one, and that was going through all of, you know, what we knew of Gurmos and calculating what the expected performance it would be for the future Gemini MCAO system, right? And so
the Osiris curve on there is with current AO?
yes.
Thanks.
Yeah, I think having looked at a few cases, when you go from Osiris and current AO to Liger plus Kappa, it's, you know, it's a mix. Kappa gets you a lot of the way down here, and Liger then gets you another, you know, pretty good chunk. Another big part of it is the slicer mode with Osiris is really a lot more sensitive than the lenslet 100 milliarc second scale with Osiris. Both at sort of fixed area and in an absolute sense. You gain a lot of surface brightness sensitivity with the slicer. And then at shorter wavelengths, especially, you know, going to from the single grading to the multi gradings.
So do you have an estimate of how many kilometers a second your velocity resolution, or meters per second your velocity resolution at the highest mode would be?
Well, at R of 10,000, you know, your full width half max would be 30 kilometers per second. And then of course, you know, you could, you know, get centroiding precision to really well, but you can resolve lines separated by 30 kilometers a second.
Juan, did you do a simulation to show the RV precision improvement?
Yeah, you should be able to get better than 1 kilometers per second RV precision. And for the velocity with precision, so the simulations I did was for looking at black hole masses in the centers, for basically for like intermediate mass black holes. And so the biggest advantage of the high spectral resolution is the higher order moments of the Gaussian Hermite distributions. And those you really gain a lot in the higher spectral resolutions. But that's using multiple lines, right? I guess the answer is different depending on whether you get only one line or multiple lines.
Well, Tucker, I think we're about almost close to time.
Yeah, I think so. Just a few minutes until roll back to the main session, right?
Yeah.
Great. Well, if we've hit everybody questions, we can go ahead and call it.
Thanks, Tucker.
Okay, thanks everyone. And please feel free to get in touch, you know, anytime, as I said, if you're interested in following this up. Thank you.
Thanks, Jelly.
Bye, guys.